Welcome back to Discrete Math. I'm Dr. Jeff Groh. In this lecture, we're going to talk about rules of inference. We'll begin with a definition. An argument is a sequence of propositions called premises that end with a premise, a proposition called the conclusion. One thing I'd like to point out is that some arguments are valid, some arguments are not valid. An argument is valid if the conclusion, the truth of the conclusion, necessarily follows from the premises. Rules of inference are tools for determining the truth of statements. We're going to begin by looking at something called Modus Ponens. In this case, we're going to start with the implication P implies Q. We're going to then assume that P is true. If P is true, then Q must be true, so we will deduce that Q is true. That's how modus ponens works. You have some implication, P implies Q. You assume that P is true. If P is true, you conclude then that Q is true. So for instance, if I am in Paris, then I am in France. I am in Paris, therefore I am in France. We could rewrite this as P implies Q and P, therefore Q. We call this the law of detachment, and this is Latin for mode that affirms. Here's another definition. A tautology is a statement that is true based on its form alone. So, for instance, how about if it is cold, then it is cold. It is cold, therefore it's cold. Well, yeah. How about water is water? Okay. I should mention that modus ponens is itself a tautology. P implies Q and P, therefore Q. Yeah, it's true based upon its form all on its own. So, modus ponens. Would be one example, and we'll show you some others, of such a tautology. Another example of a tautology is, how about this? P or not P. Either it's true or it's not. Well, that's true no matter whether P is true or not. If P is true, you get true or false, which is true. If it's false, then you get false or not false, which is true, and therefore true. No matter what you plug in for P, you'll get a true result from this. The truth table will just be true and true, regardless of the value of P. I guess we could also throw in that example, P implies P. Yeah, things imply themselves typically. Before moving along, I want to confirm that Modus Ponens is a tautology. And remember, Modus Ponens is P implies Q and P implies Q. Notice that this is equivalent to, whenever you have A implies B, that's equivalent to not A or B. And so we have this. Let's keep simplifying this. P implies Q is, of course, not P or Q. And so we have all of this not here or Q. And so we can distribute and form not P and P, which is always false, or Q and P, or Q. Well, false or something else would be just the something else, and we're taking the not of that. When we distribute the not, this will be the, let me just write this as not Q and P, or Q. This will be not Q or not P or Q. And as you can see, we can commute these around and write this as not Q or Q or not P. Well, not Q or Q must always be true. And it's true, or it doesn't really matter whatever you have here, and so you get true. So this implication, this argument, is true based on its logical form alone. That means that it is a tautology. In our next example, I want to determine if the following argument is valid and whether the conclusion must be true because of the validity of the argument. In this particular example that I'm about to write down, it will be an example where the argument is valid, but the conclusion is false because one of the premises is also false. And so this is the statement of the problem here. If the square root of 2 is greater than 3/2, then when we square both sides, we'll have 2 is greater than 9/4. The argument goes, we know the square root of 2 is greater than 3/2. Therefore, 2 is greater than 9/4. Now, the form of the argument is in the form of a modus ponens. However, when it says we know this is true, that's actually not true. Remember, the square root of 2 is approximately 1.414, rounded to some decimal place. I use a dot over the equal sign when I'm rounding some real number to some decimal place accuracy. And this is not greater than 3/2, which is 1.5. It's smaller than 1.5. And so this is false. One of our premises in this argument is false. Therefore, the conclusion doesn't necessarily follow either. In this case, the conclusion is false. 9/4 is exactly 2.25. So that's in the wrong direction as well. So the way that we'll state this is the argument is valid, but the conclusion is false because one of the premises is false. Let me write that down. The argument is valid. It's a valid form of argument, modus ponens. But the conclusion is false because one of the premises is also false. So let's look at some other rules of inference. First of all, we have modus ponens. It's in the form P implies Q, P, therefore Q. P implies Q and P implies Q. Another way of writing the same thing. It's called modus tollens. And it goes like this. P implies Q, not Q, therefore not P. If you had P implies Q as a valid, as a true implication, and Q did not hold, you can deduce that P doesn't hold either, because if it did hold, then Q would have to hold, not Q. And so we can again write this as P implies Q and not Q, and those two together imply not P. And we could prove that this also is a tautology in the same way that we proved that the argument modus ponens is a tautology. Another form of inference is called disjunctive syllogism. And it goes like this. P or Q, not P, therefore Q. If either P or Q must be true, and you know that P is false, that means that Q, in fact, must be true. And we can easily write that as P or Q and not P implies Q. And this might be a little clearer, that this P or Q and not P means that Q implies Q, which is clearly a tautology. Our fourth form of argument is hypothetical syllogism. And it goes like this. P implies Q and Q implies R, therefore P implies R. You can clearly rewrite this as P implies Q and Q implies R, and those two imply P implies R. We also have a principle called addition, and it goes like this: P, therefore P or Q. If you already know P is true, then it doesn't matter what Q is. You can add any other number of things on here using an OR statement, and you'll still get something that's true. P implies P or Q. That's another way of expressing that same thing. There's a similar idea in terms of simplification. Suppose you know P and Q. If you know that these are both true, then you know P is true. So P and Q implies P. Our seventh form of argument is called conjunction. And it goes like this: suppose P is true, suppose Q is true, therefore P and Q is true. So we can do it like this: P and Q implies P and Q, which is obviously a tautology. We also have something called resolution. Suppose you know that P or Q is true. Either P is true or Q is true. And then you know not P is true or R is true. So what does that imply? Well, it implies that either Q is true or R is true. And we can put this as P or Q and not P or R implies Q or R. That makes it perhaps a little more clear. Let me give you an example. Suppose we encounter the argument it is sunny and warm. Therefore, it is warm. So here we have sunny and warm. We deduce then that it is warm. This is a form of the simplification argument. Here's another example. If it is Friday, then we eat fish. If we eat fish, then I do the dishes. Therefore, if it is Friday, then I do the dishes. So this is the hypothetical syllogism. P implies Q, and Q implies R, therefore P implies R. In the next example, we're going to use the rules of inference to build an argument. Suppose that we're given the following 4 premises. The first premise is it is not sunny this afternoon. And it is colder than it was yesterday. The second premise is we will go swimming only if it is sunny. Then if we do not go swimming, then we will take a canoe trip. The last premise that we're going to write down is that if we take a canoe trip, then we will be home by sundown. And so from number 1, we have this assertion: it is not sunny this afternoon, and it is colder than yesterday. So from 1, we can deduce by the argument of simplification that it is not sunny. So 1 gives us, by simplification, the assertion it is not sunny. And on number 2, we will go swimming only if it is sunny. So if we had said, if it is sunny, then we will go swimming, that would be that one implication, but we didn't say that. We said we will go swimming only if it is sunny. So what we have here is swimming implies sunny. But we already have not sunny, from which we can deduce by Modus Tollens that we are not swimming. So we've used the argument of simplification, and we've used the argument Modus Tollens to deduce that we are not swimming. On part 3, we have not swimming implies canoe trip. We already know that we're not swimming. And so we can deduce that we are going to canoe, but this argument, we have this initial implication followed by the confirmation of this hypothesis. Therefore, we reach this conclusion using modus ponens. Finally, we have part 4, which is canoe implies we're home by sundown. We already know canoe, therefore we'll be home by sundown, again by a modus ponens. In the next example, we're going to suppose 1, Janet is skiing or not snowing. It is snowing, or Ralph is playing hockey. And third, Janet is skiing, or Ralph is playing hockey. So we can arrive at 3 using 1 and 2 and the principle of resolution. Remember, that was P or Q, not P or R, therefore Q or R. Janet is skiing, or it is not snowing. That's in this form here, the not snowing, P being the snowing, R being Janet is skiing. It is snowing, P, or Ralph is playing hockey. Therefore, either Janet is skiing or Ralph is playing hockey. So we can have 1 and 2 imply number 3 using the form of argument called resolution. In our next example, I want to show that P and Q or R together with R implies S. I want to show that these imply P or S. And so into the solution to this problem, I want to note that R implies S is the same thing as not R or S. So we're going to write these premises here as P and Q or R and not R or S. So by resolution, here we have an R or this, here we have a not R or this. We deduce that we have P and Q or S. Well, we can rewrite this as P or S and Q or S. So by simplification, we can think of this as P or S. These both have to be true, so in particular the first one must be true. We've shown you a number of valid forms of argument. We're now going to discuss common fallacies. These are arguments that people try to make, but these arguments are not valid. They do not lead to these tautologies that we've been talking about. The first one is affirming the conclusion. We start off with P implies Q, Q therefore P, but the implication doesn't work this way. And so this is an invalid form of argument, and it's called affirming the conclusion. Let me give you a quick example. If I am in Paris, then I am in France. I am in France, therefore I am in Paris. But that's not necessarily true. I could be in Marseille, or I could be anywhere in France. And so this form of argument is false. A second form of common fallacy is denying the hypothesis. It goes like this. P implies Q, not P, therefore not Q. So in this case, let's look at our Paris and France situation. We're saying, if I am in Paris, then I am in France. Okay, that's fine. I'm saying I'm not in Paris. Can I then therefore conclude that I'm not in France? Well, shoot, it could be someplace else in France if I'm not in Paris. So this is not a valid form of argument denying the hypothesis. There are rules of inference for statements with quantifiers. Our first form of argument is going to be universal instantiation. And it goes like this. Suppose we know for all of x, p of x. Well, if a statement is true always, it'll be true on some particular instance. So if it's true for all x, then it's true for a particular given x. Then we have universal generalization. And it goes like this. Suppose we know P of C for any C. Therefore, for all of x, P of x. You see, if we can use any C and get P of C to be true, then it's true for all values that you can plug in. Just like we had universal instantiation, we're going to have existential instantiation. And it goes like this. If there exists x such that P of x is true, then P of C is true not everywhere, but for some C. And we also have existential generalization, which works this backwards. If it's true that P of C for some C, we can deduce then that there exists x such that P of x. In our next example, I want to show that the following statements, every student in this discrete math class has been admitted to college. And John is in this class. I want to show that these two things imply the conclusion that John has been admitted to college. So number one can be written as, for all x, P of x implies Q of x. So P of x means x is in the class, and Q of x means x is admitted to college. Then we say John is in this class. So P of C. So we know that there's this principle of universal instantiation that we could apply, that P of C implies Q of C by universal instantiation. And then we have P of C is true, so by modus ponens, we get Q of C is also true. So John has been admitted to college. In this next example, I'm going to suppose that a student in this class did not watch video 6 for module 1. And then every student passed exam 1. Can I imply then that a student passed exam 1 without watching video 6? And yes, but let's lay out the steps in the argument. Number 1 is a student in this class did not watch video 6. And so there exists some student such that student is in the class and student did not watch video 6. So P of X means X in the class. Q of X means X watched video 6. And so not Q of X would be not watched video 6. By existential instantiation, we can conclude from the above that P of C and not Q of C for some C. There is a student who is in this class and who did not watch video 6. The third step in our argument is to conclude then that P of C, we know that both of these have to be true, so one part of it is true by simplification. On step 4 of our argument, we're going to convert 2 into some statement. For all x, P of X implies R of X. So if the student is in the class, then they passed exam 1. So that's what it means for every student passed exam 1. For all x, if they are students, then they passed exam 1. We can use universal instantiation to show that P of C implies R of C for any C. No matter who it is, if they're in the class, then they passed exam 1. So on step 6 of our argument, we're going to note that we already have P of C, therefore R of C by modus ponens. We're still trying to prove that some student passed exam 1 without watching video 6. So on part 7, we're going to go back to the conclusion over here in part 2 and conclude not Q of C by simplification. So this is not true. The student did not watch video 6 by simplification. So on step 8 of our argument, we're going to note that we have R of C and we also have not Q of C. So by conjunction, we'll have R of C and not Q of C. We finally get to the conclusion of the argument. There exists X such that R of X passed and did not view video 6 by existential generalization. There are only a couple of other forms of argument, valid forms of argument, that I would like to introduce. One is universal Modus Ponens, which goes like this. For all x, P of x implies Q of x. P of C, therefore Q of C. So if it is always true that P of x implies Q of x, and you know P is true for some particular value of C, you can use this then to deduce that Q is true for that value of C. The proof of this universal form of modus ponens uses universal instantiation, of course. There is then a universal modus tollens, which goes like this. For all x, P of x implies Q of x. Not Q of C, therefore not P of C. So if it is always true that P implies Q, but Q is not true for some particular value of C, then you can deduce that P is not true for that particular value of C as well, using the principle of universal instantiation and modus tollens.